Hello and welcome back. In this short session we are going to discuss identity and inverse elements, and that's all we're going to talk about in this session. It'll be a fairly short session. These concepts will be needed later to define algebraic structures such as groups, and those things will be needed when you start studying concepts in analysis. So we will limit ourselves to identity and inverse elements in this session. Let's start by defining an arbitrary binary operation O times on the set X. Since O times is a binary operation, it takes two inputs, so its inputs are elements of the Cartesian product of X with itself. They are ordered pairs in X squared, and they map back to X. It's on the set X. Now, with that definition, we can explain what an identity element is. An identity element of the operation O times is any element U that's a member of the set X, such that for all X in X, the following holds true. X O times U equals X, and U O times X equals X. And these are called right and left identity, respectively. So let's look at an example for addition on the natural numbers. Let's try the identity element U equals 0. So now for any X in a set of natural numbers, X plus 0 equals X. So that holds true. So 0 is a right identity element of the addition operation on natural numbers. And it's a left identity as well, because 0 plus X equals X for all elements in the set of natural numbers. Now that we know what identity elements are, we can define inverse elements. An inverse element xi is an inverse of another element x in the set uppercase X if, under operation O times, and we're using the same binary operation, arbitrary binary operation O times we were before, xi is an inverse element of the element x if xi O times x equals our identity element u. In fact, xi O times x equals u implies that xi is a left inverse of the element x, and if x O times xi equals u, xi is a right inverse of the element x. Typically, both will hold true, and if xi is both a left and right inverse of element x, we will call xi just the inverse element of x. Now, the inverse is with respect to the operation O times, defined, the binary operation O times defined on the set X. Let's look at an example. Let's look at addition on the real numbers. So we know for addition our identity element u equals 0. So we must have xi plus x equals 0 on the set of real numbers. So when does this hold true? If we have any element x in the real numbers, we have to add something to get 0. It turns out that we can just take the negative number in the case of our real numbers and our addition operation. So x plus negative x equals 0, and negative x plus x equals 0. So the negative of x is the inverse element of the addition operation of real numbers, both left and right inverse. So it's just the inverse element on real numbers. And we will look at a few other sets in subsequent slides. Now, I've already used the term additive identity, but let's officially define it here. An identity element of the addition operation is called an additive identity. Typically, this is called the additive identity. Now, we have seen addition defined for different types of sets. The addition operation on the natural numbers, for example, mapping ordered pairs of n squared back to n, we saw that the identity element is 0 because x plus 0 equals x for any member of the set of natural numbers. This is also true for rational and real numbers. Now, we had also defined addition on the Boolean domain. We saw that the OR operation is called Boolean addition. We also saw that Boolean addition is not exactly the same thing as addition on natural numbers. It's similar, but it's not the same. The question now is, what is, if there is at all, an additive identity? What is the additive identity for Boolean addition? And we can just try, of course, the natural thing to try would be to see if x or 0 produces x, and that is in fact the case. X or 0 or x plus x on Boolean numbers produces x for all members x in the Boolean domain. So 0 is also the Boolean additive identity. So depending on how addition is defined and what set you're operating on, you may or may not have the same identity element. You may not have an identity element at all. But in case of the addition operations that we have talked about so far, in each case the 0 element is the additive identity. So we've already seen an example of an inverse element for the addition operation. Now officially we call inverse elements of the addition operation additive inverses. So remember that our element plus our inverse element needs to be equal to, the result needs to be equal to the additive identity element, which is 0. We can do this on several sets that we've seen with the negative number. So minus x plus x equals 0 for any number in the set of whole numbers, rational numbers, or real numbers. Turns out that we do not have an additive inverse for the set of natural numbers, and that is because we don't have the negative numbers. For example, take the number 2 in the set of natural numbers. So 2 plus something would have to equal 0, but there is no negative 2, so there is no additive. There is no element inside the set of natural numbers that satisfies this condition. Now let's look at the Boolean domain. Is there such thing as an additive inverse for Boolean numbers? Remember, we had defined Boolean addition as the OR operation. Let's try the negative of our number x, Boolean number x. So negative on Booleans is not, the not operation. So if x is 0, not x equals 1. If x is 1, not x equals 0. Now remember, for the OR operation to be true, we need truth in either input, the left or the right. So if x is 0, then not x equals 1, so we're going to get 1. And if x is 1, then not x equals 0. So we're going to get a 1 no matter what. The output is always 1. And that is not the additive identity. Remember that for the Boolean OR operation, our additive identity is the 0 element. So there is no additive inverse for Boolean addition as long as we define it as the OR operation. Turns out we can define addition in a different way for Boolean numbers. We'll take a look at later. But for the definition of Boolean addition as the OR operation that we've seen, there is no additive inverse. Now we've seen an example already of the identity element under the multiplication operation, and now we'll officially define that the identity element for the multiplication operation is called the multiplicative identity. We saw on natural numbers already, so we saw that it's the number 1. So any element lowercase x of the set of natural numbers times identity element 1 returns the element x. So multiplication times 1 equals the original element, and that means that 1 is the multiplicative identity for natural, rational, and real numbers. Now, how about the Boolean numbers? Remember that we had defined the AND operation as Boolean multiplication, and we saw that it is actually equivalent to multiplication on the natural numbers if we restrict ourselves to the numbers 0 and 1. So it is in fact also the case that the element 1 in the Boolean domain is the AND identity or the multiplicative identity. So it holds true for Boolean numbers as well. Let's consider the binary operation of multiplication. So we have a left and right operand to the multiplication operation. We have defined multiplication on a number of sets, including Booleans, real numbers, rational numbers, and natural numbers. Now let's look at the multiplicative inverse of an element. The multiplicative inverse of an element is the inverse of that element under the multiplication operation. And remember, what we need now is our element times the inverse element needs to equal the identity element of that operation. And for multiplication we had identity element 1. So let's consider reals and rational numbers at the moment. So we have an element x times the inverse must equal 1. So for that to be the case, in rationals and real numbers we can take the number 1 over x. Right? So for example, the number 2 times 1 over 2 equals 1. 3 times 1 over 3 equals 1. So this works for the rational and real numbers, except for the number 0. The number 0 does not have an inverse because you cannot divide by 0. Now let's look at natural numbers. On natural numbers we don't have the number 1 over x, except when that number is 1. 1 over 1 equals 1, and that is an element of the set of natural numbers. So in case of natural numbers, our multiplicative inverse only exists for a single element, and that's the number 1. None of the other elements of the set of natural numbers have a multiplicative inverse. And the same is true for Boolean multiplication as we defined it. Remember, it was equivalent to multiplication of natural numbers if we restrict ourselves to just the numbers 0 and 1. So in case of Boolean numbers, one of the numbers of the Boolean domain, there are only 2 numbers in the Boolean domain, only one of those has a multiplicative inverse or an AND inverse, and that's the number 1. Remember, we had previously defined propositions, axioms, and identities. A proposition was a statement that's either always true or always false. An axiom was a proposition that is true, so a statement that is always true, and an identity was a axiom with an equal sign. So a proposition that's always true containing an equal sign is an identity. This is a different use of the word identity. We just talked about identity elements, and it turns out that identity elements form 2 identity axioms. Because we know from our discussion of identity elements, let's take a look at the Boolean domain as 2 examples. We know that for all numbers x in the Boolean domain, x or 0 equals x, or x plus 0 using Boolean addition equals x. And we know that x and 1 equals x, or x times 1 equals x. So these are always true because we had found that these identities hold for all elements in the set. Therefore, we can use our identity elements that we know for these operations to always be the case, always be true. These form identity axioms that we can later use in developing theorems and further algebra in axiomatic math. So our identity elements led to two identity axioms that we have here that we can use to do proofs and such. Let's take a moment to summarize this session. We started by introducing the concepts of identity and inverse elements. And then we saw that for the addition and multiplication operations, these were called additive and multiplicative inverses. We saw that for all the sets that we talked about, Boolean numbers, natural numbers, whole numbers, rationals, and reals, we had the identity elements for both operations. So we had identity elements for both addition and multiplication. Now, as far as inverses are concerned, we saw additive inverses for the sets of whole numbers, rational numbers, and real numbers, but we did not see an additive inverse for the Boolean numbers. When it comes to multiplicative inverses, we did not see inverses for any complete set. And that's because in the case of rationals and reals, where we did have the number 1 over x, we did not have it for the number 0. We did have inverses 1 over x for all the other elements, all the non-zero elements in the sets of rationals and reals. And in the sets of natural numbers, Booleans, and whole numbers, we saw multiplicative inverses for only one single element, and that was the element 1.